Okay, this is page 188, and we are going to talk about two sample proportion hypothesis test. And need you to pay very careful attention to this. This is one of the more challenging, well, actually, this is the most difficult hypothesis test to do all year. I'm not being funny. This one really has a tricky component to it. Not impossible to do, but easy to make a mistake because it has one thing that's completely different than what we, or it's a change. All right, so basically we're going to have two proportions and we're going to see if there's a difference. When we did means, we went HO and it was mu1 equals mu2. Well, not surprisingly, since it's proportions, it's just going to be P1 equals P2. Or we could say that there is no difference and just rearrange it so it means equals 0. And obviously, the alternative is going to be either greater than, less than, or not equal to. So where things get different is, well, I should probably back up just slightly. When we were doing this with means, we were saying, you know what? T equals X bar 1 minus X bar 2. So sample mean 1 minus sample mean 2 over standard S1 squared N1 plus S2 squared N2. That's what we did there. Well, we're working with proportions, so we know it's going to be a Z. They're always a Z. So my formula is not substantially different, but we're P1, P hat 1 for sample proportion 1 minus sample proportion 2. So that part matches up pretty nicely. And under the denominator, we have P hat C and Q hat C and the over N1 plus P hat C and Q hat C over N2. The difference is we haven't talked about this P hat C. We've never worked with that before. And so that's where the big difference is. And you go, well, wait a second. We just did confidence intervals for two sample. What's the big deal? Didn't we have the same thing? And the answer is no, we didn't. When we did a confidence interval, what was under the radical is our equation was P hat 1 minus P hat 2 plus or minus Z star. And we had P hat 1 Q hat 1 N1 plus P hat 2 Q hat 2 N2. But here we don't have the 1, we have a C. Here we don't have a 2, we have a C. So we're going to have to calculate something separate to come up with P hat combined. All right? It's a simple little formula, but it's just something separate that we've not done before. And the little formula is P hat combined equals X1 plus X2. Excuse me, these should not have a bar. X1 N1 plus X2 N2. And that's written better right here. All right. Please note, we're not adding fractions, we're just combining. And sometimes these are, and by the way, the C stands for combining. Now, a lot of times books will use the word pool or pooling, and in which case we would have changed this from a C to a P. The reason I use combine, and a lot of books will use combine, but there's kind of a discussion whether P combined or P pooled. The reason I use combined is because we calculate P values. We already have a P1, a P2, a P hat 1, and a P hat 2, and I did not want to put PP on your paper. So I basically figured there was enough P's on the paper not to add PP. So I go with P combined, all right? It just makes it a little bit easier. All right, our calculations are pretty much the same. We're going to run this just like a typical hypothesis test. So let's go ahead and look at our recipe for success. Recipe for success says, hey, we're going to write P1 equals P2. We're going to need to define our parameters. Our conditions, 2 independent random samples, N is less than 10% of the population. And what we care about, what you're going to need to do is you're going to calculate to see whether or not we have a large enough sample so that it'll be normal enough or approximately normal. And you'll have to do this for both proportions, both sets of proportions. For both samples, you'll have to check this out. All right. And please remember, once again, I know I have it in the other video as well, Q hat equals 1 minus P hat. All right. Here's our formula. There's a reminder that this is P hat C. And notice it goes in both places. And in case you're curious, and I'm sure you're not surprised, Q hat C equals 1 minus P hat C. That shouldn't be a surprise. And by the way, the calculator does this automatically, but we need to do this to show as part of showing our work. So it will do it behind the scenes, which is great, but we need to show our work. And then the rest of this, I think, is pretty straightforward because it follows our recipe that we've been using over and over again all semester long. So scenario 1, suppose that an early election campaign telephone poll of 800 registered voters shows 460 in favor of a particular candidate. Just before the election, a second poll shows only 520%, 520 of 1,000 registered voters expressing the same preference. At the 10% confidence level, is there sufficient evidence to say that the popularity has decreased? First off, we need to determine whether or not this is a test for means or a test for proportion. And initially, it might be a little bit challenging to see, but what I notice is it never ever doesn't give me a standard deviation of a population, and it doesn't give me the standard deviation of the sample. If it had given me the standard deviation of the population, we could have done a test for means. If it had given me this, we could have done a test for means. It didn't. So because it didn't, and I don't have a list of data, I'm going to need to look at doing this as a proportion. All right. So, and remember, proportion is just another word for percent. So we want to know if their percent has changed. Our null hypothesis, very easy. P1 equals P2. Our alternative, P1, they want to say whether or not it's decreased. So it started here, and they want to know if it decreased here. Because this is the first poll, did it decrease in the second poll? So we need to define our parameters. Let P1 equal the true population proportion of voters supporting the candidate in the early poll. Let P2 equal the true population proportion of voters supporting the candidate in the late poll. while we're here, let's talk about p hat 1 and p hat 2. All right. So what is p hat 1? And I know you don't have to do it here. It's not required. It just really helps. P hat 1, 800 registered voters. Well, that was the total number of them. P hat 1 equals X1 over N1. So this is going to be 800 over, excuse me. This will be 460 over 800. So P hat 1 460 divided by 800 is 0.575. I'm running out of room and it's a little bit hard to follow. I'm going to box that in. Now I'm going to do p hat 2. P hat 2 equals x2 over n2. So my second pole, and in the second pole we had 520 over 1,000. So p hat 2 equals 0.520. Now we can definitely see that the 520 is a decrease from 575, but could that happen by random chance alone, or is it statistically significant? We don't know yet. We need to go ahead at this point and we need to check our conditions. All right. So we're going to have to go N1, P1 has got to be greater than or equal to 10. And N1, Q hat 1 has also got to be greater than or equal to 10. Well, what was this one? 800 times 0.575 equals 460. We're good there. Here we're going to have 1,000 times 0.520 equals 520. Oh, excuse me. I'm making a bad mistake. I'm so sorry. This is 800 times, this is Q hat, so 1 minus the 0.575. And I end up getting 240. That's greater than 10, so this is met. So now I need to do this for the second sample, which is going to be into p hat 2 has to be greater than or equal to 10, into q hat 2 has got to be greater than or equal to 10. So my sample size was 1,000 times 0.520 equals 520. That's plenty big enough. Then here we have 1,000 times 1 minus the 0.520. And with that equals 480. So that's big enough. So the sample is large enough to use the normal approximation. All right. Samples are large enough. So that's what you're checking for. Large enough. And you know what? I want to put the word both in front because both samples have to be. Matter of fact, if they weren't, you wouldn't have to run the test. All right. So what's our equation? Our equation is Z equals P hat 1 minus P hat 2. Be careful. P hat C, Q hat C over N1 plus P hat C, Q hat C over N2. And we're still missing something that we need really badly. we'll start plugging in our values that we have because we know some of these, and let's see what we're missing. So what do we have? Well, we know p hat 1 is 0.575, so that's good. We know p hat 2 is 0.520, so that's good. So we've got the numerator done, so that's good. Now we have the denominator. And the good news is I have some of the denominator. I have N1 and I have N2. I know N2 is 1,000, and I know N1 was 800. But I don't have P hat C and Q hat C. So I have to calculate them. So here we go. Q hat C, that formula for P hat C is X1 plus X2 over N1 plus N2. This is 460, 800 plus 1,000, and this is 520. So P hat C equals, if I add those up, 460 plus the 520, I end up getting 980 over 1,800. And that equals 0.5444. So here's what I'm going to write. P hat C, 0.5444, and then 1 minus 0.5444. Over here, it's exactly the same thing. 0.5444 times 1 minus 0.544. And congratulations, you have now set up the most difficult test that we do all year long, right there. That's the most difficult one. So here we go. We're going to run this thing. So we're going to go stat, test, and we're going to scroll down to 2 proportion z-test right here at number 6. And what did we plug in for? What was our x1? 460. Our n1, 800. Our x2, 520. Our n2, 1,000. And we used a less than symbol, so we need to make sure we have that in there. We ended up calculating, and look at all this junk that we calculated. And there's that 0.544 that I told you was going to come up. Told you to do it behind the scenes for us. And you have to be really careful of this. We end up getting a p-value. We'll come back to that in just a second. They told us our alpha level was going to be 0.10. But my p-value is this value right here, 0.0009. 0.0099. Well, that 99 is definitely less than 1,000. So we're going to reject the null. What was the null? That the poles hadn't changed. The alternative was it had decreased. So we need to write up our conclusion. Our p-value is 0.009, excuse me, 0.0099. We reject the null. There is plenty, lots and lots of it. Enough. We like to use the word sufficient. There is sufficient evidence at alpha equal 0.10 to suggest that the true population difference in proportion of voters. Which order did we go? Early minus late. Oh, true population proportion of voters. It's not a confidence interval. True population proportion of voters was, what was our alternative? Our alternative was a greater than. Was greater earlier than later in the campaign or in the voting. Okay. So let me back up on this because kind of mess that up a little bit. Our p-value is 0.0099. We reject the null. There's plenty of evidence at alpha equal 0.01 to suggest that the true population or proportion of voters was greater earlier than later in the campaign, or the true population proportion of voters supporting the candidate was greater earlier than later. And if you left off the in campaign, that would be fine too. In other words, the candidate is losing support. All right, thank you.